Enzyme Tales. Lysine Jr. discovers ATP Synthase by Ashlyn Jensen. This is Lysine Jr., a 5th grade student at Amino Elementary. She's an excellent student with a bright future. But she has no idea what she wants to do after graduation. Her mom's been telling her to go into healthcare, and her father's been suggesting construction, but she wants to do something really important. Today, her teacher, Mrs. Myrna, is taking the class on a field trip to the mitochondrial factory to learn about energy production. Lysine Jr. is feeling really positive about going, although she is almost always positive, and so she hums on the way to school while thinking about the mitochondrial factory. Do-do-do, do-do-do. Once Lysine Jr. gets to school, she sees her teacher already waiting by the bus. Then she hops on the bus, and not too long after, they're on their way. Once they get to the factory, they're greeted by a tour guide, who begins to tell them all about the factory and the energy production. Lysine Jr. learns all about the electron transport chain production line and chemiosmosis. 20 minutes later. And then Lysine Jr. sees the biggest, most beautiful complex she has ever laid her eyes on. Lysine Jr. sees the ATP Synthase enzyme, and the tour guide begins to talk about it. ATP Synthase synthesizes ATP by bringing together ADP and inorganic phosphate. This enzyme is comprised of two main parts. The F0 component acts like a water turbine and pumps protons counterclockwise from high concentration in the intermembrane space to low concentration in the mitochondrial matrix. This generates the energy needed for the F1 component to use. The F1 component of the enzyme is comprised of 3 beta subunits and 3 alpha subunits. The reactions occur within the beta subunits due to its conformational changes during the F0 rotation. When looking down at the F1 component, you can better visualize the different subunits, which are broken into 3 types based on their conformations. First, you can see the loose conformation, denoted by the orange subunits. After a 120-degree rotation, those subunits change their conformation to the tight conformation, shown in blue. After another 120-degree rotation, the conformation changes to the open conformation, in purple. The cycle will then continue to repeat. During the loose conformation, the reactants ADP and PI enter. In the tight conformation, the reaction to form ATP occurs, and then finally, in the open conformation, the product ATP is released. During the loose conformation, adenosine diphosphate and inorganic phosphate diffuse into the beta subunit. They are held in place by a series of hydrogen bonds by amino acids in the P loop. Some of these amino acids include glutamic acid, lysine, and arginine. A magnesium 2+ ion plays an important role in neutralizing the charges on the inorganic phosphate and ADP. This forms the intermediate MgADP. During the tight conformation, the magnesium ion continues to stabilize the negative charges on the reactants. This is crucial in minimizing the negative-negative repulsions felt by each molecule during the nucleophilic attack. The negatively charged oxygen of ADP attacks the phosphorus on the inorganic phosphate, in turn causing water to be removed and leave as a leaving group. Once the ATP is formed, the conformation changes once again, becoming the open conformation. Here, the molecule ATP becomes planar and the magnesium lets go to form the final product. It is then ejected from the beta subunit. This is an incredibly important process as energy is needed for everything. To harness this energy created, the reaction will simply be reversed and chop that phosphate group back off. It will then come back here to be reused. Quite the job stability. Lysine sat in awe watching ATP synthase at work and listening to the tour guide explain it. She knew at that very moment she was no longer confused, and she was going to become part of the ATP synthase P loop. The end.